So types of errors and power. So we have two types of error. We have what we call the type 1 error and we have the called type 2 error. Type 1 error is the rejection of a true null hypothesis, while type 2 error is failing to reject the null hypothesis when it's actually false. So you can see a table showing it here. So imagine your null hypothesis is true and you now decided to reject it. You have committed a type 1 error. If you notice that a null hypothesis is false and you fail to reject it, you have committed a type 2 error. So probability of committing a type 1 error is alpha, while probability of committing a type 2 error is beta. The probability of rejecting null hypothesis when actually false is now going to be the power of the study, which is 1 minus beta. So some of the key points are that you cannot know the truth with certainty. So we control error rates through study design, and also your sample size affects type 2 error. So your sample size affects your type 2 error. So that's why I can see that what the power is very important when calculating the sample size. When you reject the null hypothesis when it's actually true. Then example, concluding a drug works when it actually does not. So this is an example now. Imagine you find out that a drug is working when it actually doesn't work. We usually give the probability of committing this error as 0.05 or 5%. So this means 5% chance of false positive. And it's controlled by the significance level, and multiple testing increases type 1 error. So alpha is usually set before the conducting the study and it remains fixed. So type 2 error is probability of failing to reject the null hypothesis when it's actually false. So this one we usually set it as 0.2. And if we set it as 0.2, it means the power is now going to be 1 minus beta, which is 0.8. So that means 20% chance of missing a real effect. And it's affected primarily by sample size and also affected by effect size and variability. So the beta usually decreases as sample size increases. So statistical power is the probability of correctly rejecting the null hypothesis when it is false. So if your beta is 0.2, then your power becomes 1 minus beta, which is 0.8. So this means 80% chance of detecting a real effect. So conventional standard, the minimum acceptable is usually 80% the power. Preferably, if you can use 90% power or a high power of 95%. So what are the factors that affect power? Power increases when your sample sizes increases, usually most controllable. And also when your effect sizes also increases, your power is also likely to increase. When significance level also increases, then your power is also likely to increase, but increase your chance of getting false positive. That's your chance of committing type 1 error, which is rejecting the null hypothesis when it's actually true. Also, your variability in your data decreases, so for better measurements or homogeneous sample. So the trade-off is that higher power requires larger sample size or accepting more type 1 errors. So you have to choose between accepting more type 1 error by having higher power, because if you have higher power, your likely chance of committing type 2 error reduces, but that of getting type 1 error increases. So what power curve shows? So how power changes with sample size, the diminishing return of larger samples, and also how effect size impacts required sample size. The typical pattern is like this: a steep increase initially, then levels off at a larger sample size, then different curves for different effect size. I'm going to be showing you the diagram, how power changes with sample size. So you can see this is an example of a diagram now. On our x-axis, we have the sample size per group, then we have the statistical power. So you can see at this lower sample size, the power is increasing. Then when you go to around 50, you can see the power has increased to 0. This should be around 0.7. You can see around 80% power. Then the sample size starts from, this should be around 70 something. If you can see that this should be around 70 something sample size. So our goal now in this graph, we're trying to look for the minimum sample size that we can use to get the maximum power. You can see that 80% power, we're getting around 70 something. So that means we can start with 70 something as our sample size. If you need more power and you have the ability to collect more sample size, you can go to as high as 100. So 100 is approaching close to 1. The power is close to 1. I can see our effect size here is 0.5 D in this place. So this is how the power curve actually looks like, and lets you know the minimum sample size you can take to get the maximum power. So in medical screening, type 2 error is usually more serious. So type 2 error is where you fail to reject your null hypothesis when it's actually false. So, and it's more serious because failing to reject a null hypothesis, it means that a particular drug is not effective when it's actually effective. So it's likely that you're going to what miss a disease. Your alpha is also going to be set to 0.1 to reduce beta. You might need to set alpha to 0.1. So what you're trying to do now is that you are setting a lower probability of committing a type 1 error to 0.1 so that you're going to reduce the value of beta. So you accept more false positives to catch more cases. Also, in terms of drug approval, so type 1 error is more serious, approving ineffective or harmful drug, and you keep strict alpha is equals to 0.05 or lower. In type 1 error, you reject another hypothesis when is what one is actually true, which means that what you are approving a drug that is ineffective or harmful, you are approving it as what effective. So this is very dangerous. So these are the various contexts of both type 1 and type 2 error.